Welcome back, and this is a Fourier series synthesizer which I got made, and it runs in Python, and it's just to illustrate Fourier series and actually as a sine wave generator and just show you what's possible again, sort of things you can do at home. And it's got 5 sine wave generators all in phase and 5 cosine generators all in phase, 5 here, top 5 and the bottom 5. That's not really enough for a decent Fourier series, but it's enough just to show what's going on, just for the basic principle. It's also got some triggering in it, like an oscilloscope. I was quite surprised when the AI managed to do that without any trouble, really. Again, it was done relatively quickly. I tell a slight lie there, because it wasn't done that quickly to begin with, because I was using the wrong AI program. I hadn't realised. As soon as I switched to the O1 Mini, everything worked perfectly, but before then there was errors and so on and so forth. And lots of apologies from the AI, but once I shifted it was okay. So how does this work? Well, it should be running at the moment. So we could just, there's a first sine wave. They're all defaulted to 100 Hertz, but I can change that. So the first one I'll just put up. And I don't know if you can hear that. You should be able to hear it. That's the 100 Hertz. You see how it's at least trying to trigger. It's a bit like a scope. There's a trigger threshold, a trigger edge. It's on the rising edge of the waveform. Just triggering on the positive side. Anything less than 1 should do. I can put a DC offset in as well. It makes much difference. Take that out. And I can change the frequency. Say 1 kilohertz. And I can zoom the time axis. It doesn't go any lower than that's the lowest resolution, but I can change that if I need to. Yeah, I can't remember what it's at now too. Let's make it 0.02. That's better. Right. Bit loud. So let's put in a second frequency very close to the first. But I'll make this smaller. 0.5 amplitude. The second one also, well, about 0.4, doesn't matter. And the second frequency will make 110. So we should get a beat frequency. I'll make it 105. It's a beat frequency now. You can't hear it that well because it's such a low frequency, but it's like having an amplitude modulated signal. To illustrate it better, oh, I know why I've done that. Sorry, I've put the wrong way. The first one's at 1 kilohertz, so it should be 1005. There it is. You can hear the beat frequency now. And if I make this wider, see, it looks a bit like an amplitude modulated wave. It's the sum of 2 sine waves, but it's not really, but that's what it looks like. Let's get rid of that. Oh. Let's go back to 100 Hertz because it's less on the ears. It's quite nasty. So let's make a square wave, which is just sine waves. It's got fundamental, let's say 100 Hertz. The second harmonic, it's got nothing of its symmetric. Third harmonic is a third, so 0.33. And it's at 200 Hertz. That's the second harmonic. You can hear it coming in. And then there's nothing on the fourth, it's 0 again. And the fifth is a fifth or 0.2, and that should third harmonic should have been 300. It's better. And the fifth harmonic is 500. And the reason it doesn't look like a square wave is because there's a sort of reset thing you've got to do. There. Now that's a little bit more like a square wave, but I'll zoom in on it. And there you can see the classic sort of Gibbs phenomenon, but it's not many terms in the series, of course, you know, to look like a decent square wave, but you can see it beginning to work. So one thing I can do on this, I'll just turn, how do I turn it off? I should have an off switch. That's better. One thing I can do is I can store all the settings in what's called a JSON file. Here it is for the square wave. A JSON file is just like a glorified spreadsheet, but with delimiters so that you can read it. It can have all sorts of things in it. It's got curly brackets to define what's the external sides of it, beginning and the end, and then the various things you define, the amplitudes, frequencies, and so on. These are used a lot, the JSON files nowadays. So what I'm going to do is, I've already done a few things. Let's load some settings on the desktop. I've got a triangular wave. Now the triangular wave, again, doesn't look much like a triangular. I'm going to go out and come in again. Yeah, but that's better. Some sort of reset thing, I don't know what it is, a glitch there. That's a triangular wave, and that only uses the cosine terms. There's no sine terms in there at all. I just got that off the web. I mean, it didn't bother working it out, but if you look at my book, which is called Rudiments of Signal Processing and Systems, I've got a whole, I don't know, I think it's probably a whole chapter on Fourier series. It is kind of important for electrical engineers to know about Fourier series. Let's do another one. Here's another square. There's another square wave, but this time at 500 hertz. And again, I'll zoom in on it. Oh, it won't go any lower. Yeah, 500 hertz. Let's look at another one. Another triangular one, but this time again I need to. It doesn't look like a triangular one there, does it? But it is. What it is it's a triangular, and then nothing, and then a triangle, and then nothing. It goes flat, and then up, down. As long as it's a periodic function, and it satisfies certain conditions, which in electrical engineering it nearly always does. Most of our waveforms are continuous. They don't have funny things in them. Then it should be able to get a Fourier series, but it must be periodic with a defined period. So that's a kind of triangular wave. This one's supposed to be a half-wave rectifier, half-wave rectified. You can see it's beginning to look like that. Sort of coming up and down, but again, there's not enough points to define it. But that's the basic idea anyway. Oh, here's the thing. Can that's the least annoying, I think. No, actually, I think let's get rid of those. Let's just put 100 hertz, amplitude 1. And I'm just going to see if I can link in my spectrum analyzer into it. It should, in theory, link in through the computer, but it doesn't always work out that easily. So we've got to put the right input device. to nothing. Anyway, so that's a Fourier series generator. You might be asking, why didn't I make this? Why didn't I make this with knobs on, so to speak, a bit like LabVIEW? And the answer to that is I did, and it made a good job of it. But when you put all these extra things on with Python, it's in real time. It's not really a real time even MicroPython isn't that great compared with C++. But it had a nice. Oh, that's the wrong one I'm looking at. I'm looking for the Fourier series one. Oh, I don't have it. Sorry, I must have overwritten it. But actually, it was rather good. But it was very, very slow, so I had to get rid of it in the end. So there it is. Fourier series. Make your own. You could make a synthesizer if you wanted to as well. That would be quite interesting. But again, if you start putting in control knobs and things, it's going to be very slow unless you've got a super fast computer. Compiling it makes it a little bit faster. I was reading up about this, but not that much faster. I'm afraid that's just the way it goes, these languages. It's never going to run as fast as something like C++. Okay, thank you very much for that. Bye-bye.